Good morning, good afternoon, good evening, wherever you may be in this part of the world, and welcome to another session of my presentation series. And this time, the topic is the site acceptance testing of a power transformer. That is when you are going to install a power transformer during the project, right? And basically, you have to perform the site inspection and electrical testing of the power transformer. And my good name is John Kweku Amotu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Okay, so if you watch my presentation and you like it, don't forget to select the like button and share, and also select the subscribe button at my YouTube channel. And below is my YouTube channel, Work and Happiness Talking to the Engineer. Okay, so visit there. There's a lot of tons of presentations out there that will be beneficial for your career, and for you young engineers out there, that will also be very good for you in your career, basically, and learning the technical and the field experience as part of your career development. Okay, so now let's take a deep dive into the site acceptance testing that you are supposed to do. Okay, so once a power transformer completes factory acceptance testing at the factory, right? Okay, so basically, the manufacturer will ship this power transformer to the customer project site, right? Okay, so when it goes there, basically, and depending on the size of the transformer, if it is a really big transformer, right? What happens, let's take an example for a free breathing transformer or consider a tank transformer. A transformer with a consider tank, right? Okay, so the consider tank will be dismantled, right? And the piping from the consider tank, where we have the Buchholz device, will also be disassembled, right? Okay, then the radiators will also be disassembled, right? Okay, then the bushings will also be disassembled, right? Then, the top of the transformer will be capped where the bushings are located, or will be capped. The only components that will be the auxiliaries, the oil gauge, temperature gauge, the winding temperature gauge, the oil level gauge, yeah, and also the control box, right? The cubicle where basically all the wiring interface with from the transformer comes in, and from here it goes to an RTU to your SCADA system, right? Okay, so that one will be kept on the transformer, but it's going to be padded, right, to prevent damage during transportation. Then the oil in the transformer will all be drained and put in gallons, right? Okay. Then the transformer will be filled with air, right? Very dry air, and dew monitor will be installed on it to measure the amount of moisture intrusion that goes in during transit of shipping. Okay, so once the transformer gets there, and also for transformers that are greater than 20 tons and above, okay, they have an accelerometer that is basically impact recorder that is installed on this transformer. Basically, that measures gravitational acceleration, in different vertical, horizontal, then radial, right, direction. So when it gets there, basically, you basically send it back to the manufacturer to analyze these gravitational forces to determine if there is any damage during transit of the transformer. Okay, so once the transformer gets there, remember, I told you all the components that are removed and basically packaged nicely, right there, and basically to prevent damage. Once it gets there, you as the discipline engineer, right, maintenance engineer, operational engineer, maintenance technician, operational technician, right, project engineer, project manager, it is your job to take a look at all these shipping pieces, right? They'll all be listed, right, for you to check these components to make sure there is no damage to these components, right? And all the nameplate or anything that is basically imprinted matches with design. Okay. So what you do is basically you plan for the installation of these transformer, right? Okay, so during installation, they install the transformer, they install all the components, right? Okay, and we took an example of free breathing transformer, transformer with a consider tank, right? There are two types of, we have the seal, right, and the free breathing. The seal type is basically where On top of the oil, you have basically nitrogen blanket, basically that is acting as a positive, creating a positive pressure on the oil, right? Okay, so once this transformer is installed, next what you need to do is first do operational tests and check of the auxiliary devices. And these are the auxiliary devices, the oil temperature indicator, basically that is looking at the top oil temperature, right? You do operational test and check. Then similarly for the winding indicator, right? You do that to determine the hottest spot. Then all the oil level gauges, right? Okay, so we'll have an oil level gauge for the main tank, and also for the considered tank, we'll have an oil level gauge for it. And if you have a radiator, if you have an OLTC, right, we also have an oil level gauge in the OLTC. Next is the air breather silica gel, which is for the free breathing, right? Then the cooling fans and the oil pumps. Okay, so oil pumps, some of the transformers, based on the size of the transformer, oil pumps are used. Then the solid pressure relays, right? Those are located on the sides of the transformer, right? That is able to detect incipient, right? Gradually evolving faults, right? Okay, because some of the faults are what might not develop enough current. The driving voltage for the voltage is so small that it basically will not be able to generate enough current, so the differential might not see. So that is when the solid pressure relay is able to detect this fault. On the other hand, if you should have a through fault, that pressure wave, high pressure wave due to the high electrodynamic forces created by the short circuit current, right, will be sensed by the bellows of the solid pressure relay. Next is the pressure relief device, right, that is mounted on top of the power transformer, that is able to basically the last sort of protection for the transformer based on evolving pressure if all the protection schemes on the power transformer should fail. Next is the Buchholz device, right? The Buchholz device is located in the downcoming piping from the considered tank to the main tank, and it has three functions. The first one is to be able to detect low-level oil, right? If you run out of oil in the main tank, right, and this one replenishes, right, and this one runs out of oil at a certain level, it will give an alarm, and low oil level, it will trip the transformer out of service. Next is to be able to determine, basically isolate, alarm the transformer based on incipient gassing, right? If you have broken connections, broken strands, tank shorts, right, that will lead to certain gases being generated, right? Acetylene, carbon monoxide, etc., etc. And this gassing, because they are so lighter, will rise up and accumulate into a chamber in the Buchholz device. And based on the volume of accumulation of the gas, it is going to activate a mercury switch that will provide an alarm, for action to be taken, investigation to be performed to validate it. Right. Okay. So then the simulation of the integration of all these devices and the alarm circuits to either a SCADA system, right, or a central control room, right, a centralized operational center, right. All this, the whole part of that alarm and trips will be checked. Next is the performance of insulation resistance of the control circuit, right. 250 volts DC or 500 volts DC is utilized to test these control circuits to make sure there's no damage to the insulation of this control circuits. Next is a check of the OLTC. So now let's talk about the testing, right? First one is a capacitance test, right? Okay, so capacitance testing is done, right, in addition to tan delta test, right? Okay, it's where basically, like I told you, that the active component of the power transformer, that is the insulation system, the thermally upgraded paper, the solid insulation and the liquid insulation, they are all arranged in such a way that they create a capacitance network. We have a high voltage to ground capacitance, low voltage to ground capacitance, and high voltage to low voltage capacitance, right? So basically, the arrangement tells you the geometrical configuration of the active component based on the capacitance that this insulation system and the conductor and the ground plane for, right? Okay, so we perform, they call it AC diagnosis testing, right? We perform the testing of this capacitance and the tan delta, that is power factor, right? The power factor, we are determining the contamination level of both the solid paper, thermally upgraded paper, and the oil in the transformer. So we compare the testing results with the nameplate data, especially the capacitance, right? Or the factory acceptance testing results to determine if there's any delta, right? If you have a delta greater than 10%, then that should be a concern that you have to investigate. Right? A delta shouldn't be greater than 5%. 5% is the criteria for a change in capacitance, right? Okay, so if you experience or have results that shows capacitance greater than 10%, then there are other testing that you have to do to confirm that indeed you have a change in the geometry of the active component. An active component is the core and coil of the transformer, including the clamping structures. Next is the test ratio. Okay, so the test ratio, basically what we are doing is to determine if you have 10 shorts, you have broken connections of the tap changer. You have any broken strands inside the transformer, right? So what it's doing is the high voltage to the low voltage voltage that gives you your test ratio. That is V1 over V2 is equal to N1 over N2, right? And N1 over N2 is equal to I2 over I1, right? That gives you your test ratio. Next is vector group, right? Okay, so when we do the test ratio, we also determine the vector group, right? The vector group, let's say for a DYN1 transformer, right? You have the high voltage wound in a delta configuration, and we have the low voltage wound in a Y ground configuration, right? And the grounding could either be solidly grounded or resistance grounded or reactor grounded, right? And the one basically shows the phase shift between the high voltage side and the low voltage side. So this one we have a 1. That means that the high voltage side leads the low voltage side by 30 degrees. On the other hand, if we have 11 here, that means that the low voltage side leads the high voltage side by 30 degrees because 11 is 30 degrees, right? Okay. So when we do the test ratio, that is when we check the vector group, and we also perform the polarity, right? So the polarity will be the direction and an instantaneous value of the current, right? So for the high voltage side, we have current going in, and for the low voltage side, we have current coming out. So that is what we check for. Next is the winding resistance, right? Okay, so the winding resistance, we do the testing where basically we inject, DC current and basically measure the corresponding voltage. Then from there, we determine the winding resistance. So we do the winding resistance for each phase and compare the resistance in each phase and make sure that it does not deviate more than 2%, right? Anything greater than 4% over with the average means that, or phase to phase, that means that you have to do further investigations to determine the cause of that. Next is a magnetic balance, right? Magnetic balance test that basically is able to determine the path, right, of the magnetic flux, right, to determine that there is no, the magnetic path is balanced, right? Okay, so the flux that is flowing in A, B, C, right? Okay, A and C should be balanced, right? And B, so the flux that is flowing here should be greater than what is flowing in A and B. So that is what they call the magnetic balance test. Next is vibration, right? Okay, so the vibration, this is when the structural engineers comes into play, right? Okay, to make sure that, the transformer whilst it's in operation, because the active component, right, energization and all those things, it creates vibration, right? And the foundation that the transformer sits on should be able to withstand this vibration for throughout the whole life cycle of its of the transformer, right? So the structural engineers do all the testing to make sure, and also there's something they call natural resonance, right? They capture all the vibration signals to make sure that there is no natural frequency that will coincide with any other natural frequency to resonate and cause a breakdown of the foundation and any other structures that is in the transformer. Next is sweep frequency response analysis, right? Okay, so sweep frequency response analysis is performed because the transformer is shipped from the factory, right? Okay, so you do that testing to make sure there is no internal damage to the transformer, right? Okay, if there's any shifting of the active component, that is the core and the winding and the clamping structure, that will manifest itself in the sweep frequency response fingerprint chart. You overlay the current results with the fingerprint results during the factory acceptance test time. Next is the extension current. Extension current is done to identify if there are any shorts in the laminations, right? Okay, so for the laminations, right, you have right here. You have a limb A, the central limb, right here. So what you do is you do that testing, and basically you determine the extension current that is flowing through the magnetization branch of the transformer, right? Okay, so you have the reactor here, then the resistance here, right? Okay, so you have the R and the X, the inductance. Okay, so you determine that amount of extension current that is flowing in through this magnetization branch to determine if there's any defects in your laminations, right? Okay, the laminations basically forms the magnetization branch of the power transformer, and your goal is to determine if there are any insulation degradation, insulation defects, any shorts in between the laminations, any damage, any path to ground, right? And also turns to 10 shorts, trans damage, right? Okay, so that is what you do the extension current test. Next is short circuit impedance, right? Okay, so that is your leakage impedance plus your resistance, then you calculate your Z, right? Okay, so you compare this testing with what is performed in the factory during the factory acceptance testing. The goal is to make sure that there's no deviation between 7.5%, right? That is the deviation. So you always compare the testing results with what is performed earlier on, or what is performed in the factory during the factory acceptance testing. Next is insulation resistance. Okay, so you do the insulation resistance to determine the contamination level, right? And also perform the polarization index, right? Where you divide the insulation resistance at 10 minutes over the insulation resistance at 1 minute, right? To determine the contamination level on both the paper, the solid insulation, and the oil insulation. The goal is basically, the criteria is for a new transformer is to get a polarization index of greater than 2.0. Right. For in-service transformer, all you need is something greater than 1.5 and above. Anything below 1.5 and below for the polarization index requires further investigation. Right. So with that, that comes to the end of my presentation. Thank you so much for your listening. Yes, and look out for my other coming presentations. Right, and also don't forget to select the like button on my YouTube channel, and also subscribe my YouTube channel. With that, thank you so much.